Welcome to the Control Engineering and Plant Engineering webcast. Develop an industrial robotic specification by using this checklist, sponsored by Universal Robots. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering, Plant Engineering, and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed as approval or endorsement by RCEP. In this course, we will discuss how to determine when industrial robots should be considered and who should be involved in robot selection, discover what kind of industrial robots can be used for what applications, review industrial robot specification best practices, develop a checklist of selection criteria for industrial robots, compare readiness to survey respondents as a benchmark. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you're having technical problems, click on the question mark at the top right corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you're experiencing issues with your slide or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to your technical questions will be in the Answered Questions box on the left side of your screen. You can use the Ask a Question box on the left side of your screen to type questions for the presenters during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation. We'll get to as many as time allows. Questions that are for today's presenters will be answered verbally during the Q&A session at the end of the webcast. To download the presentation slides, use the Event Resources area on the left side of your screen. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted on the on-demand version of the webcast. The exam is for one RCEP ACEC Certified Professional Development Hour. The webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering and Plant Engineering websites in a few days, and we'll send you an email with the link to the archive once it's ready. The method of delivery and category. This event is a live educational webcast presented on October 29th, 2019. The educational category is Technical Health and Safety. Now a word from our sponsor, Universal Robots. Today's webinar is sponsored by Universal Robots, the leading global manufacturer of collaborative robots. Universal Robots was founded in 2005 with the goal of making automation accessible to everyone. To date, Universal Robots is the fastest growing collaborative cobot manufacturer, having sold over 37,000 worldwide. This equates to a 55 to 60% global market share. Universal Robots is known for being flexible and easy to program, enabling UR cobots to be used in a wide variety of industries and applications. From packaging to screw driving and inspection, from machine tending to gluing and welding, UR is the cobot of choice. Universal Robots sets the industry standard for cobots. They are fast to set up, have flexible deployment, are easy to program, and their collaborative nature lowers risk. UR keeps its product line simple with only 4 robot models, ranging from the smallest UR3E with a 3 kilogram payload to its newest and heaviest payload, the new UR16E, which boasts an impressive 35-pound payload. Learn more about cobots from Universal Robots. Visit their website at www.universal-robots.com or call 1-844-462-6268. That ends the commercial. Thank you to our sponsor. We welcome today Ian Mogab, Senior Sales Engineer with Patty Engineering, who has 5 years of industrial automation experience in engineering, consulting, marketing, and sales, finding innovative solutions that apply leading technology to solve manufacturing challenges. Project experience includes robotics, machine vision, plant floor automation and controls, industrial networking, and RFID. He holds a Bachelor of Science degree in Engineering Technology from Texas A&M University. Ryan Wasman, Sales and Marketing Director at Concept Systems, began as a robotics engineer with more than 15 years ago for a robotic integrator with an automotive focus. He worked for an aerospace industry manufacturer in engineering, robotics, machine vision, 3D scanning, and robotic standardization. He served as division automation manager at a metal fabrication company. He has a Bachelor of Applied Science in Electrical, Electronics, and Communications Engineering and Associates in Science and Computer Systems, Networking, and Telecommunication from ITT Technical Institute of Portland. I'm moderator and research presenter for today, Mark T. Husky, Control Engineering Content Manager. Ian, please go ahead.
Thanks, Mark. First, we will determine when industrial robots should be considered and who should be involved in robot selection. We will cover identifying process opportunities, determining if a robot is a good solution to those opportunities, defining system feasibility, how much robot costs to implement, and finally, how a return on investment is realized. We must first identify problems or opportunities within our process. I often tell the manufacturers that we work with that you shouldn't have a solution looking for a problem. Walking around your facility looking for places that you can put a robot will often lead to a failed project or a project that never even gets off the ground. Instead, we should look at our process and identify areas where it can be improved. Once we find areas of improvement, we can consider solutions, which may be robotics or maybe something completely different depending on the application. We can now determine if a robot is a good fit to solve the problem or improve the process. These will fall into either economic or non-economic justifications. Economic justification means that by implementing this solution, we will directly save or make more money. Labor is a good example. You might be trying to address high labor costs, or you aren't able to hire enough skilled workers to achieve the desired output. Alternatively, you might see an opportunity to increase your manufacturing efficiency with the same workforce. Oftentimes, robots can work faster or more efficiently than humans, allowing for higher outputs in a given period of time. Non-economic justifications are projects that are influenced by factors that don't directly save or make us money, although oftentimes these have long-term financial impacts as well. Robots can be used in situations where humans cannot feasibly perform the task due to safety or ergonomic concerns. Robot repeatability can improve quality significantly, and robot flexibility can help manufacturers adapt to changing market conditions quickly. Many projects will have more than one or even all of these justifications in a single project. It is important to be able to assign a dollar value to each of these. We'll come back to this later when talking about return on investment. Once we have determined if this is a problem that a robot may be able to address, we need to figure out if a robot is able to achieve the task from an engineering perspective. There are many factors to consider here, but some of the basics are checking for floor space availability, part payload, reach requirements, and part variations. This is usually done in collaboration with your systems integrator or internal robotics team. If we have determined that this problem is one that a robot can address and the project is technically feasible, we must then determine if the cost of implementing the robot cell is acceptable. Here we must look at the total cost of a robotic system and not just the robot itself. Within a robot cell, you will need to consider that there is often part transfer systems, cell controls, end effectors, guarding, safety devices, integration, as well as many other components. A general guideline that we use is the robot price tends to be about 1/5 of a complete robotics system. However, this is just a guideline and can vary dramatically depending on the application. At this point, if we know the robot can solve our problem and we have determined the cost required to implement the robot cell, we just need to determine if it is worth it to us to implement this robot cell by calculating a return on investment. We'll need to go back to our original justifications and add them all up. It is important to consider all of the potential gains and not just the ones that result in direct cost savings. From here, each company usually has a standard way of calculating return on investment for capital projects, and usually they have targets that they are trying to achieve. In general, implementing industrial robotics has a high upfront cost with a longer-term payback period. However, the very low operating and maintenance costs of a well-implemented robot cell can provide great value long-term once the capital cost has been recovered. Once you've decided you're going to implement a robot in your facility, you will need to create a specification for that cell. We'll go over who should be involved in that. Usually when implementing a robot cell, there is an internal team who oversees developing the specifications and requirements for the cell. In addition, there will be a robotics integrator or an internal robotics team assigned with implementing the cell to meet the provided specifications. From the end user side, we usually see the following people involved. Manufacturing engineering should consult on available space and how the cell should be laid out. Industrial or process engineering should provide cycle time and sequence of operations information. Maintenance should weigh in on specific part types so there is a spare part compatibility across the plant. Safety should be consulted on any company or plant-specific robotic safety requirements. Controls engineering will need to communicate with the robot and interface with existing control systems. Purchasing will need to provide feedback on budgets and suppliers. And finally, operations should be consulted for each of these steps because they are the ones that ultimately have to work with the robot cell long term. Once the robot cell specification has been developed, it is the integrator's job to take this specification, determine if the specifications are technically feasible, and if it can be accomplished within the end user's budget. To do this, they may do a reach study, create a draft cell layout, or even do a complete robot simulation. How this is accomplished depends on the integrator, how difficult the task is, and how much risk is involved. Oftentimes, there is some back and forth between the end user and integrator to come to an agreement on a specification that is technically feasible, within budget, and accomplishes all of the end user's key goals. Once this is accomplished, the integrator can then begin developing solution specifics, such as which robot will be used, how the cell will function, and so on. Next, we will talk about the types of industrial robots and what applications they can be used for. We'll cover 5 of the most common types here, and then a few more will be presented in the research slides at the end of the presentation. The first type of robot is probably the one that comes to mind for most people when thinking of industrial robotics, articulating robots. These typically have 6 axes, but there are other configurations available. Articulating robots are one of the most flexible styles of robots in that they can be programmed for many different operations. Most commonly used for pick and place, machine tending, assembly, packaging, palletizing, as well as other operations noted on the right side of the screen. Articulating robots also have the best ability to articulate into and around obstacles, as well as work on different planes due to their joints. The large selection of reaches and payloads also means there are models for small to very large projects. On the flip side, articulating robots are generally expensive compared to other types of robots. Their additional axes make them slower and more difficult to recover from faults than other types of robots. Selected compliance articulated robot arms, also called SCARA robots, typically have 4 axes. SCARA robots are usually very lightweight and have a small footprint. Their rigid Z-axis is one of their key features that makes them great for tight tolerance vertical tasks. Common operations for SCARA robots are pick and place, assembly, and inspection tasks. SCARA robots are very limited by their usually low payloads and small reach. They have a fixed swing arm, which also allows for very limited articulation into and around obstacles. Cartesian or Gantry robots are one of the most common types of robot. They usually consist of 1 to 3 linear joints, and a very common configuration is XYZ axes. Cartesian robots are usually very low cost compared to other types of robots. They are highly customizable in size, speed, and payload for small to very large applications. Additionally, in unique applications, a Cartesian robot can be combined with another type of robot as an end effector for additional flexibility and articulation. Cartesian robots are often used for pick and place, assembly, inspection, and dispensing applications. Cartesian robots and their custom nature can make programming and design much more complicated, and their exposed actuators do not function well in dirty environments. Their linear joints also make it difficult to articulate into and around obstacles. Delta robots are a type of parallelogram robot with typically 3 or 4 axes. They excel in very high-speed operations, and their small footprint and inverted mounting is great for retrofits of existing conveyors. Delta robots are very commonly used in pick-and-place, assembly, and inspection operations, most commonly in conveyor applications. The downsides of a Delta robot are its very limited reach and very low payloads. The last type of robot I will go over here is one that is much newer to the industrial robotics space. Autonomous mobile robots are wheeled robots that use software and sensors to guide the robot and avoid obstacles. These robots are almost always used for material transport. However, in unique applications, they can be combined with another type of robot to perform other operations. Autonomous mobile robots provide much more autonomy and flexibility than an AGV type system, which must follow a strict route typically installed in the floor. Autonomous mobile robots can also navigate around obstacles on their own. The main downside of them is they run at lower speeds than typical human-driven vehicles. Now, a lot of you might be thinking I missed collaborative robots during my list of robot types. I did that on purpose in order to highlight that collaborative robots are not necessarily a type of robot, but more so a type of robot system. A collaborative robot system is defined by the task that the robot is performing and the space in which that task is being done. Many of the robots listed earlier can be part of a collaborative robot system if the system is properly designed. A traditional robot system utilizes barriers for complete separation between human and robot. In systems like this, humans and robots only interact during maintenance or programming. These type of systems are often still required, especially in cases where high speeds, large loads, or hazardous materials are involved. Collaborative robot systems can often be considered in applications where a comprehensive risk assessment has been completed and deemed the entire system safe. ISO 15066 for collaborative robots defines 4 types of collaborative robots. There's safety rated monitored stop, where safety systems stop robots upon humans entering the work envelope and automatically resume the robots upon humans leaving the work envelope. Speed and separation monitoring, where safety systems slow robots when humans enter the work envelope and stop the robot completely when in immediate proximity to the robot. There's power and force limiting robots, where system design eliminates pinch points and collision sensors limit force. These are the type that most manufacturers have branded as collaborative robots. However, just because a robot is branded as collaborative does not mean the entire system is collaborative, and a risk assessment must still be completed. Finally, there are hand guiding robots, which are equipped with a hand guiding device which an operator can use to control the motion of the robot during automatic mode. These type are often used for lift assist type applications. These 4 types defined in ISO 15066 are just guidelines, and it is very important that a qualified person perform a comprehensive risk assessment before implementing any collaborative robot cell. Thank you. Now Ryan will address the next 2 learning objectives.
Thank you, Ian. So for this learning objective, view industrial robot specification best practices. We're just going to take a look at a few of the specifications. One thing that I can't stress enough is that these bullets are used as a reference specifically to design a robotic specification. Some of the things included in a robotic specification should be scope, standards internal to your company, critical requirements that are necessary for the cell to be successful, environmental concerns, testing of the cell, timeline, points of contact. This isn't an inclusive list, but definitely can be used as a point of reference. The main objective of the industrial robotics specification is to set your expectations early for designing a system. These things should include the functional design of the system, timeline that you're expecting the system to be installed and proven in, what types of robots or control systems need to be in place, the types of communications that the system is going to use, and what type of workmanship standards. Also, something else to think about is when you're setting your expectations, proposal layout. So explaining to the system integrator that you're working with how you'd like to see the information that they're proposing to you laid out so that you can make good decisions and get apples to apples comparisons. Also included in that is the timeline for when the expected proposal should be received and testing requirements, if any, for the cell that you're working in. Another thing to think about at this step as a best practice is including a risk assessment. All cells have to have a risk assessment. This comes standard set by RIA in the US, ISO internationally, and OSHA, who enforces these standards. The goal of a risk assessment, we'll get into that later, is very important. It's to keep our workers safe and make sure that the cell functions as intended and all risks are thought through. So to cover developing a checklist of selection criteria for industrial robots, we're going to get into some specifics in what goes into the industrial robotic specification. So when you're developing a robotic work cell, there's a good checklist to use, which is identifying the problem, mapping the tasks for that problem, aligning these requirements, defining the layout of the cell, identifying any and all safety hazards associated with the cell, and defining the deliverables that are required to make this a successful endeavor. So step one, identifying the problem. The first thing that you should do when you're identifying a problem inside your plant is developing a problem statement. That means really, truly defining what are you trying to solve. Those things should come along with an executive summary. So what business drivers are you trying to meet? What type of metrics are you looking to use to measure the success of the problem being solved? What type of internal costs and return you're looking for? And really, truly defining project stakeholders early on in the project. So if you're developing a checklist, you really want to make sure that operations is involved in helping with the problem identification, also EHS in helping with identifying any safety risks and helping with improving those safety risks during the remediation phase of the project. Engineering team is involved to make sure that the right parts are being selected and the right metrics are being met, and finance to ensure that your cost and return will meet the plant standard. At this point, a lot of work will go into mapping the tasks for this associated work cell. So if you have parts identified, and you now know that this is a specific type of application, which could be material handling, pick, pack, pal, welding, material removal, identifying the actual operation and those parts that go through that operation. At this point, you want to sequence your operation, and you want to identify current state versus future state. So what do you really want this cell to do for you? What do you want this operation to look like when you're done with the automation? And at this point, you really need to develop a takt time study. A takt time study is going to give you the ability to measure your current state and all of the workflow that goes into that current state so that you can make an estimate of your cost savings and ultimately measure your return on investment. Some of the things that you also want to do are part flow, which will allow you to determine how long parts are taking to move from process to process and simplify that process. And then value stream map, which is going to give you any waste streams associated with this process so that you can also capture some of that for your return on investment. At this point, you need to sit down with your stakeholder team and you need to talk through the requirements for the robotic work cell. As Ian mentioned earlier, the robot type, if you have standards, the manufacturer, the payload, the precision, and the cycle time and reach of the robot, these are all critical things to define for the robot selection to ensure that the robot can meet the requirements that you laid out. Defining an end-of-arm tool, which depends on functionality. There's end-of-arm tools that are very simple, gripper systems to completely complex engineering efforts that are entire work cells on the end of a robot. So really defining your end-of-arm tool and what it needs to do, the precision that it needs to have is critical. Also defining requirements for the peripheral systems. Do we need a machine vision cell that can do quality checks? Do we need data collection in the cell? Is there cell controls that need to be put in place so that we can drive systems upstream or downstream of the robotic work cell that we're installing? What type of safety systems do we need in place? Are they area scanners, light curtains, hand one button or two button press, depending on the type of application? There's quite a bit that goes into safety. Manufacturing execution system. So really understanding and defining where the data is flowing into this cell and out of this cell. If you have a manufacturing execution system where part data will be read into the cell and the robotic tasks will be performed based on this incoming information. If you're writing information back to an MES or ERP system, really making sure that those things are defined up front. And then testing. Critical to define testing requirements for a work cell so that the company that's helping you with that work cell, or even your internal team that's helping to put this work cell together, really has a solid understanding of what success looks like, and then factory and site acceptance testing being defined as when the cell is built, what does it need to meet the requirements in order for the plant to accept this work cell. At this point, you should have a very solid understanding of the tasks that the robot is to perform, the parts that the robot is going to be working through, and you should be able to now define the layout of the cell. Some fundamental things to think about when you're defining the layout of the cell is the location of the cell. Where will the cell go in the current process? Do we need to move this cell into the current process? Will it impact production? Do we need to build it next to the existing system and move parts into that cell? So thinking through the location of the cell internal to the plant, some of the foundation requirements. So if you're doing a large material handling project with a very, very large robot, it could weigh over 8,000 or 9,000 pounds, and it could require a 6 to 8 inch thick slab of concrete with reinforced steel bar running through the concrete. So really need to understand the foundational requirements, what utilities are required. If you need air, if you need water, if you need some kind of process gas, those things need to be required. Those things they need to be defined and laid out in the system layout in a utilities matrix. And ergonomics, what height do things need to be at for somebody to work with that cell properly? If operators are interfacing with the cell often, definitely need to consider ergonomics. User interface and HMI, so think of things like how simplistic does the layout need to be so that an operator can operate the cell efficiently and quickly, and if there's a problem with the cell, get that information so that they can resolve the problem quickly. Access points, bringing parts in and out, maintenance access points. So if a robot needs to have maintenance done to it, or end of arm tool needs to have maintenance done to it, are there points in the cell that somebody can get into and out of the cell efficiently without having any injuries sustained or any kind of obstructions? Safety interface locations, so emergency stops, push buttons, start stops, where those get placed. These are all important things to think about when you're defining the layout of the cell. Also, areas around the cell for WIP storage, work in process storage. So parts that are going to enter the cell or parts that have been processed through the cell that need to exit the cell. If there's some kind of a queue, where does that queue go, and is there room for that queue? And then just in general, thinking about part flow to and from the cell. At this point, defining your safety risk and remediation plan is important. There's a very good document, the RA 1506-2012 standard, that helps you understand how to perform a risk assessment. There's companies that can help you with risk assessment, but one thing I want to stress is that the end user is responsible for the functional safety of a work cell. So if you hire an integrator to install a work cell, they should be doing a risk assessment, but it should also be signed off on by your team internally at your facility. Some of the things included in identifying the hazards are the process for setup of parts. So you're not just thinking about safety while the cell's running, but if I have to enter the cell, do I have to stand on top of something in order to set up a part? How can I mitigate that risk? There's production things to think about. If the robot's moving at a certain speed, and it's holding a part, does it wield some kind of an object at the end of the cell, at the end of the robot arm? Then you need to protect the cell in a different way than if it's moving at a slow speed. Maintenance. So if you're doing maintenance in the cell, around the cell, or if there's hazardous gases that are being introduced in the cell, how do you lock out and tag out those things so that all hazardous energy is removed from the cell prior to doing maintenance? In the risk assessment process, you'll identify severity and occurrence of these hazards, and by taking the hazard, the severity, and the occurrence, you'll identify it with a certain risk level, and then you have to work down to get that risk mitigated to the point where it's acceptable for the RA or ISO standard. At this point, defining deliverables is critical. So when you have a system and you need to do something with it at some point later, having a drawings package of that system is critical to your maintenance staff, is critical to your production team if they want to introduce new parts, manuals for the operation of the cell, code. So when you're thinking about asking for a deliverable, sometimes the source code or the programming is important to get from the team that put this cell together, whether it's the internal team or a system integrator. Having that code stored somewhere is important so that you can make updates and changes without being stuck with a black box system. Asking for spare parts. What kind of critical spares do we need for this system? What type of preventative maintenance schedules do we have in place? How often do I need to do maintenance on this system? What type of mean time to repair do we have? And some other things are good to define as deliverables for the cell. Testing results. If you required testing for development or FAT or SAT, having those results on file can be a critical deliverable of the cell when it's finally installed and up and running. And then on-site support and training. Those are two things that are often overlooked when developing a specification for a robotic work cell, and those are critical to the ongoing evolution of the work cell. On-site support is really key to getting the cell running smoothly and working out that final 5% of things that happen when you're installing a robotic system, and training the staff so that the engineering team can move on to the next project and the internal production staff and operations staff can manage the work cell on a day-to-day basis.
Great, thanks, Ryan. I'll present a few slides now on recent research to those here attending the webcast so that people can bench their experiences to the survey respondents from control engineering and plant engineering robotic research. So a 2019 survey of control engineering and plant engineering subscribers asked questions about the use of robots and related hardware, software, peripherals, robotic safety, training, installation, integration, maintenance, trends, and purchasing habits. I offer some thanks to CFE Media and Technology Research Director Amanda Pelliccioni and Hemdeep Kaur, CFE Media Audience Database Technician, for their work on this project, and other staff, and to the Robotics Industries Association for reviewing many survey questions. Thanks also to the patient 118 respondents who buy or specify or influence robots or robotic hardware, software, services, or training. 5 data points from the study and their answers follow below. On the following 5 questions, respondents could check all that apply, and I'm only showing the top respondents. The full research report will have all the information. I did try to cut off where there was a drop of more than a few percentage points. Also, at the time I was putting this together, I didn't have the margin of error for the research, but usually it's in the plus or minus 4 to 6% range. The point is, don't get hung up on a few percentage points either way, but focus on the trends. So for the top 7 types of robots that respondents buy or specify, articulated robots remain the large majority of robots at 72%. Robots operating collaboratively, 32%, 28% gantry robots, 28% mobile robots, 28% collaborate robots. Those are designed to be speed or force limiting in such a way to minimize risk to humans. And then 28% Cartesian robots and 15% SCARA. Other robots include autonomous industrial drones, parallelogram drones, including Delta robots, robotic exoskeletons for assembly logistics or to decrease repetitive motion or movement tasks, hybrid robots, and others. I do think it's interesting that adding together the robots designed for collaborative use and those modified for collaborative use make the speed and force limiting robotic applications a strong second on the list at 60%. Since all the collaboratively designed robots I've seen so far are articulated robots, these also could be counted in the articulated robot section. I also like how mobile robots are right up there with Gantry and Cartesian. I'm unsure a mobile robot would have made the top 7 maybe 5 years ago. So those are coming on strong. Here are the top 9 robotic devices, systems, or services that respondents buy or specify. I wanted to share this answer because it shows the need for wider engineering efforts when working on robotic specifications. It's not just the robot. There's so much more to consider. Especially important is the last point. Without end-of-arm tooling, of course, any robot with an arm is just a moving enclosure of automation. So robots, 71%, 64% robot sensors or vision, 59% robot grippers, 52% robot software, 50% robots as part of a larger machine or cell, 49% robot control panels and enclosures, 45% robotic integration, and then 45% robotic power supply and 45% robotic effectors, end-of-arm tooling. Interestingly, for those responding to this survey, more are doing their own integration than hiring others to help. 45% versus 34%. It's just my observation, but it seems to me that robot manufacturers, like other automation providers, are making their offerings easier to set up and program and operate, perhaps because time to productivity has become a more important metric with demographic pressures and the skills gap. However, robotic experts, such as system integrators, can help shorten the time to productivity, whether those are experts on staff or a robot system integrator used to doing this kind of thing every day. So among the top 7 reasons behind the next robot purchase, increased throughput and quality are the runaway top reasons for the next robot purchase. So those are 64% and 52% respectively. And then a little bit further down the line, 30% to eliminate one or more bottlenecks, 30% to do dangerous things that increase risk to workers, 28% do things that we can't hire people to do, 27% save jobs by increasing competitiveness, market share to keep the facility running, and 27% to do dull things that workers usually don't want to do. So while all the topics differ, I think they generally follow the competitiveness theme, even including safety, because of course when there's downtime due to an accident, productivity isn't happening. All of these, however, seem like positive reasons for buying a robot. Safety is the topic that swings both ways. My coworker, Rick Ellis, CFE Media Technology Director for Audience Management, noted that in a separate question in the survey, a combined 56% of respondents felt that they did not have or they still need the correct amount of safety training related to robotics. So safety training, as both speakers mentioned, very important as it relates to robots. The systems have to be set up correctly, and people have to be trained appropriately on their use. So here we show the top obstacles to purchasing a robot, and then the top challenges in place for existing robots. Please note that 5 items on the left are also on the right. So, and if we count the predictive monitoring part of maintenance. So I'm glad that for robots in place, safety is not among the leading challenges. That would be disturbing if people hadn't figured out safety by the time the robots are already in place. Interestingly, though, financing and justification continues to be among the top challenges for robots in place. So as with any investment, continued attention to proving its value is needed and important after the installation takes place. All of these points tell me that those specifying robots need help, and that's part of what this research and this webcast are both designed to do. So now we have time for a question and answer session. The audience listening live can type questions for today's presenters in the Ask a Question box on the screen, and I already see some questions coming in. We'll answer as many of them as we can, and within a few days the presentation will be available for on-demand viewing along with the link to the quiz for potential PDH credit. We'll post the archive on Control Engineering's website and Plant Engineering, and we'll send a link to an email through an email message connecting directly to it and to related resources after it's ready. And now, on to the questions. Here's a question addressed to Ian. Ryan, you're certainly welcome to chime in. Can I have an integrator develop a robot specification for me?
Mark, that's a great question. You can certainly work with an integrator to develop a robot specification. In fact, we actually recommend that to make sure that both parties are on the same page. But I don't think it's something that you can just hand off 100% to an integrator. There's too much process-specific knowledge or business goals that the integrator won't be able to answer without having some feedback from you or the end user.
Good, thank you.
You touched on the, it's a partnership, right? You touched on the process piece of it, and the integrator really needs to know from the end user what those process requirements are in order to have a successful implementation.
A question addressed to Ryan. Who should be involved in a risk assessment?
So risk assessment should involve the maintenance staff. It should include operations, so whoever's going to actually operate the cell, and it should involve the integrator, whether that's external integrator or your internal integration team, and it also should involve somebody from the safety side of the business.
And then maybe a follow-up question to that would be, a risk assessment isn't a static thing, right? Those need to happen over time, especially if any changes occur.
Yeah, if so identifying the risks and then mitigating them up front before the cell is turned over to operations is a requirement. And then definitely if something changes, if new parts are introduced or some kind of maintenance task is identified that wasn't identified previously, the risk assessment should be updated to reflect those changes and the appropriate mitigation.
Another question, Ryan and Ian, what are some common incorrect assumptions when creating a robot specification? So it sounds like both of you have worked with people in helping in this task. Are there things that people just get wrong?
I can take that one. I think one of the biggest things is people think that a robot specification is a document that they have to put together to give to their integrator because it's something that they were asked for. But really, it's as much for the end user as it is for the integrator. It's the beginning of a contract so that you as the end user know exactly what you're getting, and there's no surprises at the end or you know, disagreements on what was purchased, stuff like that.
Good. Brian, anything to add?
No, I think Ian handled it well.
Okay, great. Next question, how do I know which collaborative robot I can use for my application?
So we were talking earlier about how there's 4 types of collaborative robots that have been defined by the ISO standards. Now, which one you use is very much going to come down to your risk assessment, and it's going to be very specific to your application. Just some general guidelines, the top 2, safety rated monitored stop and speed and separation monitoring, those are typically going to be used in instances where higher speeds or heavier loads are required. The power and force limiting and the hand guiding robots are usually used in situations where you've got lighter loads and slower speeds involved.
Great, thank you. At what point is it best to ask an integrator for help with the robotics project or creating a specification?
I'll take that one, Ian. I think that it's important to bring an integrator in earlier rather than later. And with that being said, I would say bring in an integrator once you've identified some of the first steps that I went through in the presentation, really identifying the problems that you're trying to solve. Maybe you've worked with your operations team and you understand where their bottlenecks are in the facility. And from there, you've identified some applications that you think robotics could be used. It's a great time at that point to bring in an integrator, possibly before you've actually put solutions on paper, or maybe you have some conceptual solutions in mind. Then it's a great opportunity to bring an integrator in.
Great, thank you. Here's a question for me. When will the full robot research results be available? More of the research results will be discussed in December issues of Control Engineering and Plant Engineering, and then the full report will be available on both websites and linked to this webcast area when it's ready. So we'll get that out as soon as we can. Let's see. For Ryan and Ian, can you each offer an example when a robot implementation might have gone better if the specification was better? In each example, what was missing that might have caused the grief? So, you know, you guys went over a lot of material, and I would imagine that you've seen projects take shape that maybe could have gone better. Could a better specification have helped, and why?
I can jump in here. I know several projects that we've had that have had issues with specifications. It's usually, like we were talking about earlier, it's issues with process specifics, things that we as an integrator don't necessarily have intimate knowledge of. So some things that we've had issues with in the past are quality specs. We weren't given accurate quality specs, or we weren't given quality specs at all. And then at the end of the project, what the customer received wasn't aligned with with what they were expecting. Also, we've had some issues in the past where there's an unknown part type that pops up halfway through the project, where we were expecting 3 different part types or something like that, and there's a 4th one that we weren't told about, stuff like that. So just having all those details nailed down ahead of time makes the project go much smoother.
Ryan, anything to
I would
add?
I would add, you know, ensuring that your testing requirements are identified, and if there's engineering development to be done during the design phase and the build phase of the cell, that parts are available that represent the part in the actual state that it will be in production. I've seen parts delivered as the test pieces, and those parts weren't in the state that they would be in production. A great example is you know, maybe a part, and we're developing some machine vision application for a part, and the finish of the part is wrong. So we develop all of our solution around that test piece to find out that the part is really shiny and not dull in the production environment. So ensuring that you get the right parts during testing and that the right testing requirements are defined.
Good. Here's a decent follow-up question to that. Have there been studies completed after implementation of robotic cells to determine if the objectives, including ROI, have been accomplished?
Usually, coming from an integrator's point of view, usually we aren't involved in those studies. Once the functional acceptance test is completed, that's where we hand it over, or the factory acceptance test is completed. That's when we kind of hand it over to the operations, train them up, and then from there, usually they're the ones maintaining the cell. But what we've heard from our customers is that usually that the ROI ranges from a couple of months to several years, with probably the most common being 1 to 2 years as far as ROI goes.
Ryan, anything to add?
Yeah, I would just add, in my previous role in manufacturing engineering and automation management in a manufacturing company, it is, like Ian said, typical that you would measure these things over time. It's good to have those metrics in place and defined for factory acceptance and site acceptance testing, so that you have a baseline to go by, and then measuring those things over time will actually give you some predictive capabilities as well to make sure the cell's going to stay up and running.
Well, thanks everyone for the great questions. We'll try to get as many of the unanswered questions offline as we can. And thanks again to our presenters, Ian Mogab and Ryan Wasman, for sharing their time and expertise. Contact information is on the slide there. Now that we're just about finished, we'd like to get your feedback. A short survey will pop up on the screen as soon as the webcast event ends. Please take a moment to complete it. We use this information to improve our webcasts. Finally, on behalf of Control Engineering and Plant Engineering, CFE Media and Technology, thank you for attending. This concludes our webcast. Thank you and goodbye.